Hello. Hi guys, good morning. Welcome back to my video. Ki hal chal? I hope you're doing good. In this, we're gonna see a problem. Count of substrings containing every vowel and k consonants too. So it simply says that again, there's a one version as well. It's a easy one. You can solve it via simple brute force. You'll see the brute force as well. So we are given a string word and a non-negative integer k. So as you can see, a string word is given and non-negative integer k is given. I have to return the total number of substrings of word that contain every vowel A, I, O, U and at least one time the vowel should be there and exactly k consonants. So isn't it simple that I can run, two for loops to just get every possible substring and then another for loop just to get what is the count of vowels in that and also the count of consonants in that. The vowel count should be at least 1 and consonant count should be exactly k. And that will take O of n cube time. Again, we have already seen many times, in many of our problems. Again, if you don't know many of what I am referring, you can simply come on to array and these are many problems which are discussed in array itself, where we have seen in this brute force solution, I can optimize this n cube to n square, which means that while I am at one of my array, one of my substring, I will try to expand it and then I can simply take the count of the next one. With that, I will just be going from I to all possible j's and then moving I one step forward and then trying for all possible j's again. So that will make us O of n square. But again, in this case, we will see that constraints of O of n square also would not work because n is 2 into 1 is 5. So how to go about it? Obviously, we have to think of in terms of O of n. But before we go on to think of in terms of O of n, let's quickly have a look at the examples. Example says that, okay, first one, I want A, I, O, U. Okay, U is not there, so it's not even possible to have a one substring itself. Answer is 0. Here, I have A, I, O, U, and the amount of constants I need is 0. That's the reason it is perfect. I have found one substring. In this case, I have A, E, I, O, U, and one constant only. So this is one possible option. Next possible option is A, E, I, O, U, and one constant. Again, I have got one option. There's one more. If you see, A, E, I, O, U, and one constant like this. So these are the three which I could find, and that is the reason it is my answer. So as you must be seeing this example, you must have clicked one thing. Aryan, I could see that this is one string, this is one substring, then this is one substring. There's a standard pattern. Pattern is that every of this, kind of substring is containing five vowels and one constant. And that's exactly what I wanted also. So isn't it that I can simply find all windows of size 6? I can just simply do a sliding window technique, right? Simple window, this is one window. Then go on and try the next window. And I will keep on maintaining the vowel count and consonant count. And with that, I will get my answer. So if you thought that, then you must read the problem again because consonant count is fixed, but vowel count can be literally anything. It is at least once. So what will happen? It will happen that if I ask you that, bro, check this thing. Now the window size is not 6, but because I have repeating number of vowels here. But still, I have to complete all the vowels. That is the reason I have to take this window. And that is the reason the window size becomes flexible. Now, did you see that when the window size becomes flexible, what is that called? That is called as two-pointer approach. So I'm expecting that you must have watched, if you would have simply go onto the website, come on to crash courses, you must have watched two-pointer crash course. I'm expecting that. If not, then please make sure that you have watched it. Coming on back, now the problem becomes a two-pointer problem rather than a sliding window problem. And we saw that why sliding window cannot be possible here. Okay, let's proceed forward. So now, as we saw that now it is two pointers, let's try to apply it. We learned a simple two-pointer approach. But in a two-pointer approach, we have a quick thing. What is a quick thing? Obviously, you have two pointers, right? L and R. Again, obviously make sure that whenever I teach, I take a very random location. Now, this is a correct window. Now, two pointer says that you will have to take some operation. Expand your R or shrink your L. That is your two operation. Do one of them. But in this case, if I expand my R, again, right now, this is a bad condition. Firstly, this is a very bad condition. Why it is valid? Because you know that my at least my vowels are at least once, and my consonant is exactly k. Primarily, consonant is exactly k, which is once. Now, the task is that what you will do. Can you expand or will you shrink? That's the question. So if I expand it, it will become like this. Again, the vowel is same, and also the vowel count is same. As in, like, the vowel condition is also satisfied, and consonant count is also exactly k. But if I shrink it, you might say, Aryan, now, oh, Aryan, now there's one thing. Now, it is not valid. Okay, so now, Aryan, you are saying that we can apply two pointers here, right? No. Why not? What if I would still have been here? Then what? Again, if you would have shrinked it, then still it's valid. So in both the cases, it is being valid. So how will you even figure out that you have to shrink or expand? And that's the exact same thing which we discussed in two-pointer approach as well. So if you come on back, you have these two problems, right? Binary sum with sum and subarray sum equal to k. Equal to k, we realized that we were actually confused if we have to shrink or expand. And that is the reason we have to go around and check that what to do. And in that, if you remember, we saw this thing that to find the answer for equal to k goal, we try for less than equal to goal, and then we subtract less than goal. Same way we will approach here. We want exactly equal to k, right? Again, we want exactly equal to k. So I will have at least k, and I will subtract at least k plus 1. Again, you can go around in the reverse manner as well, k, and then subtracting k minus 1 as well. Totally up to you, however you want to go around. So now we realize that okay, I can go. And how and why this will be valid? This will be valid because at least k will say that find all the subarrays with k, k plus 1, k plus 2 as constants. At least k plus 1 will say find all these subarrays with k plus 1, k plus 2, and so on and so forth as constants. If I subtract it, these will cancel out. I will be simply remaining with k. And that is the reason I will be able to find my answer for k. And why it is easy to find at least k? Because at least k helps me to shrink easily without any burden. What I mean by that is that that if I am, again, obviously, let's start off with a simple trial, and then I will show you also that why at least k is possible. Although if you would have seen the crash course, it would have been much easier for you. But coming on back, we realize that okay, we use a simple two pointer and we will keep on expanding r. My r is here, my r is here, at every step, no matter what. So there's one standard thing: at every step, no matter what, r will keep on expanding. R will keep on expanding. So R kept on expanding and stopped here. Why it stopped? Because now I have one valid condition. What is a valid condition? Valid condition is at least one vowel and at least one or at least k consonants. That is the reason it stopped here. Now, if I say you stopped here, how many number of subarrays? How many number of subarrays? Obviously, because it stopped here. Right now, it is a good condition. Right now, it's a good condition. So technically, always you have to make sure that okay, right now it's good. So you have to now proceed towards bad condition, which means you will shrink. That's a standard approach of two pointers. So if you shrink it, obviously things can become bad, or things, it has a possibility of becoming bad. And that is the reason your L will now shift in future. And again, when I say bad, it may become bad, because if I is still there, then these things are not yet bad. It may become bad. That's the thing. So what you did, you obviously will have to now consider this LR and find all possible substrings with this LR. So if let's say L was here, now I am here. I know that now it is valid. So I should count all possible substrings. What are all possible substrings? One is this, second is this, third is this, fourth is this, fifth is this. You see, these are all possible substrings. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is nothing but 14 minus 5. 14 minus 5 number of substrings will be there, which are valid, and also, I'm not saying ending at R, no, which are valid and also starting at L and going forward anywhere. Again, make sure the word mention says starting at L, ending, or their end start at R and go on up till end. That is the number of substring which follows this condition. And which is the reason I just simply have now my number of valid count of substring as 9. Okay. Now obviously you will proceed forward, which means you will shrink now because it is valid state. You will now shrink, and now shrinking is easy, and now shrinking is valid also because now it can be possible that I is still there. So obviously you have to maintain a hash map of vowels. That's one thing. But if you shrink now, you will now have this state. This state. Now obviously again this is again valid. So now you will again have to add. If you shrink it, you again have to add a 14 minus 5 because this will say this starting at L as 1. Cool. So again, so far, if we solve with the origin example, we have 9 possible valid substring. Obviously, I will have to shrink. As I did a shrink, I realized, oh, it is now invalid. So if it's invalid, I have to stop my shrinking. I have to now keep on expanding. Again, expanding operation happens every time. So I will just expand once. My R will become here. Then again, it's not valid so far. R will come here. Now it is again valid. If it's again valid, count the contributions. Contributions will be 14 minus 7, which is this. So I added 7. Okay, now it is again valid. If it is valid, so you have to do what? You will shrink it. If it's valid, you will shrink it. When I say shrink it, okay, you will shrink it. Now, as I shrinked it, it again became invalid. Oh, no worries. In the next iteration, R will go forward. Then we will check again. Now, R went forward. If I checked again, now it again became valid. Okay, again add a 14 minus 8, which is 6. Okay, now if it's valid, again try to shrink it. Again, when I say shrink it, I'll try to shrink one by one. Okay, I shrinked it. It again became, when I shrinked it, it again became invalid. So I will again try to expand, in the next iteration R, I expand it. Now it again became valid. So now 14 minus 9, 5. Same way, try to shrink it, expand it, add a 4. Again, same way, shrink it, expand it, 3. Now, I try to shrink it here. Again, it's valid. So what I will do? I will obviously not expand it yet. This is again valid. So simply add a 14 minus 11 again. I added that again. Okay, now because this is valid. So again, try to shrink it. Now this is the thing. If I try to shrink it, shrink and keep my L here, it is now this thing. Again, this is invalid because it needs at least K and K is 1. At least one consonant I need. So I'll expand it. Now it is valid. Okay, I added 14 minus 2, which is 2. And that's it. Because when the moment I shrink my L, then no matter how much I expand, I will not be having 5 vowels, and that's the reason this will end right here. So you see, when I said at least K, my answer was 39. When I say K is 1 here in this case. Same way, I will find for at least K plus 1, which is K equal to 2. Exact same concept, but now the K will be 2, which means I need 2 consonants now. So this is first window. So I will have a contribution of 14 minus 6, which is 8. Again, whenever the condition is good, you shrink it. And again, the beauty is only this, that now the condition is good, you can simply shrink it now. You don't have to worry about anything else. When you are fixed on one operation you can apply, then you can simply proceed with that. If you are confused, okay, I can also expand, I can also shrink, then you are actually, you will be confused. But if you have one option, you will be good to go. So now again I shrinked it, but then I have to expand it as well. So again I added 14 minus 7. Again I will try to shrink it here, but then it will become invalid. In the next iteration it will automatically go R forward. It will again be here. Again it is valid, so adding a 6. Same way, shrink it, make it invalid. Now again expand it, making R, making valid 5. Same way, again shrinking and expanding, 4. Again lastly, adding a 3, it becomes 33. Again last step, one more, I have a 2. So ultimately trying for this as well, adding a 1, it becomes 36. So 36 for K plus 1, at least K plus 1, and 39, if you remember, 39 for my at least K. That is the reason 39 minus 36, answer is 3, and that is what my answer was. If I go back, my answer was nothing but a 3 itself. Cool. So let's see the code. It's exactly same as what we have been seeing in previous questions, which is here. So what we saw that firstly we will have, and we'll call count at least for K and subtract for K plus 1. Again, this is a simple function which will check if the character is vowel or not. Now comes the main part, which is a two-pointer approach. Firstly, if you remember very basic stuff, that in any window you need to find if you have all vowels or not, And then consonant count. Consonant count can be in a variable as well, consonant count, but vowel count I will have to keep in a hash map, or in maybe a array as well. So I will keep a hash map, vowel frequency, which will maintain the frequency of A, E, I, O, U. Make sure the size will remain only 5 and it will not go beyond 5. Constant count I will have starting from 0, and then left and right pointers for my two pointer approach. Now obviously, as we know, there's a standard stuff that we always move our right pointer one step, always one step, and that is, you can also see that right pointer will always move no matter what. Now comes the fun part. As I go on to any character, any right word, I will check if it's a vowel or not. If it's a vowel, then increase the vowel frequency. If it's a consonant, then increase the consonant count. With that, my right, as I mentioned, as I, let's say, proceed towards the right. So let's take a better example. Yeah, as I proceed towards the right, so I'll just take in consideration this thing, right? And obviously, as I take in consideration, as obviously I moved my right, so I have to make sure that is the condition valid now, which means the vowel size is 5, which means I have 5 vowels at least, and also my consonant count is more than equal to k. Why it is more than equal to? Because we have chosen at least concept here. So now if it is valid, only and only if it is valid, now you can start contributing or adding the contribution in your valid count. Valid count is the number of valid substrings which starts at r and ends at r or maybe higher. That is the valid count you have. Obviously, if it's a valid count, you will incorporate how? N minus the right pointer. This is how you incorporated your number of valid substrings. Now, obviously, as I mentioned, that if things are valid, then you try to shrink. So you try to move your L forward. But obviously, if you move your L forward, before moving your L forward, whatever was there at this location, you have to remove its contribution. So if at left I had a vowel, so I will reduce its contribution. If at left I have a constant, then I will reduce its contribution. But obviously there's a small catch, that if at the left there's a vowel and then you are making the vowel frequency as 0 by reducing it, so you have to remove that from the hash map as well. Why? Because you are comparing the size of the hash map. So if there are some entities in the hash map who like are A, E, I, O, U, which means that they should be there only and only when their value is non-zero. So if it is, let's say, 2, 3, 1, 0, 4, so this even should not be there. I should only have those things in my hash map which have a value non-zero. And that is the thing why I have to make sure that I'm erasing that from my hash map if the frequency becomes 0. That's a simple shrinking case, right? And again, make sure as you remove the significance of L, you increase your L as well. Repeat the process. If it's still valid, now you will incorporate L to R, number of substrings starting from L to ending at R or higher. That you will again count and keep on counting as you have a valid L and R. And again, obviously, if you come out of this while loop, which means, okay, now you will obviously have to increase your R in the next step and then repeat the main process. That's the standard two-pointer approach, which we have seen in the template as well of two pointers. This is a two-pointer guy show. I highly recommend go and watch this as well if you don't know two pointers basics. Now, that is the ultimate thing. With that, you will simply getting the answer. Because you are now using two pointers, your time will be O of n. Because you are only using a hash map of size 5, the space will be O of 1. Cool. I hope you guys liked it. Again, brute force approach I didn't discuss. There's one O of n space approach as well. That is also, not significant. So yeah, that's your answer. I hope you guys liked it. If yes, make sure that we please hit the like target of 100 likes, and that will be lovely because it takes a bit of love for keep things encouraged. Bye bye, see you, take care. Sorry, bye bye, take care, see you.